Hello there, organic chemistry students. We're going to go ahead and we're going to make that video for the Chapter 9 homework. Again, this is the Chapter 9 homework for Chemistry 2131 Solomon's 12th edition. So in this one, we're looking at NMR and mass spec. So let's go ahead and start with identifying all the different hydrogen signals that we would see. Signals, not peaks. So we're not going to do the peak-to-peak splitting here. So we have this hydrogen, this hydrogen, this hydrogen, and these three hydrogens here. Okay, so those three hydrogens are definitely going to be a peak. So we have a peak here. This is definitely going to be a peak here. Now, we might have two because we have this is in proximity to that methyl group, and this is only next to a hydrogen. So I think we're going to have four peaks here, but these are going to be pretty close together. Okay. See how we discern that? Because remember, those are fixed in space. There's no free rotation around that double bond, so that we have to have them look through space to see if they're the same or not. All right, let's look at this one. We have proton here. We don't have a proton there. We have a proton here, but then we have symmetry. These are symmetrical. So I think we're going to have two peaks. And that way we're going to see only two peaks because we don't have protons on either of those. And this is equivalent to that, and these are equivalent to those. So we're going to have two peaks for that one. Okay, let's go to B. Sorry, I skipped over that one. Let's see, we have a hydrogen here and a hydrogen here. And notice they have the same environment. They're across from each other, and so they're probably going to be equal. And if we do a thing right here, this signal is going to be the same as that signal, because if we go around the ring, it's the same. And that's going to give us our last signal. So we're going to do one signal here, 2 and 3. So we're going to have a total of 3 signals for this one right here. Again, symmetry helps us with that. And let's look at D. You'd think we have symmetry here, but we have two different groups here. But because they're the same thing, I think these two are going to be the same peak. These two are going to be the same peak. There's no hydrogens on any of those. So we're going to have 1, 2, and this methyl group is different than that methyl group. So this is going to be 3, 4, 5. So the answer is 5 different peaks for those. Ooh, let's look at this one here. So these are definitely different than these, which is definitely different than that. So I'm going to say we have 3 peaks for this. Okay, now we have a problem here, because now we have hydrogens up. We have one hydrogen here. We have this hydrogen and this hydrogen, and then we have these two hydrogens. And then these two probably are the same signal because they have almost the same environment going either way. So let's see if we're going to have these two are going to give one signal because they're the same. This is going to give one signal because it's different than everything else. This one is going to give a different signal because it can see the oxygen through space. This one's going to give a different signal because it's going to see the hydrogen through space. So we have 1, 2, 3, 4, 5. I think we're going to have 5 peaks in that spectrum. They might be really close together though, the 4 and the 5 here, but I think we're going to see 5. Ooh, now we have a symmetry problem again. Let's see, those are going to be equal to those. And then these are going to be equal to those. And then these are going to be equal to those. And then these are going to be equal to those. And there's no hydrogen on either one of those. So I'm going to say 4 peaks for that. Okay. Ooh, we got one right here, but we got symmetry on our hands here. So let's go for that symmetry right here. And let's not forget we have hydrogens down here, hydrogen up, hydrogen down, hydrogen up, hydrogen down. Okay. So the 2 hydrogen downs here are going to make the same peak. So I'm going to circle those. Not that. These 2 hydrogens are going to be the same. Okay. And we got, don't forget the OH peaks here. That's going to be a peak there. Okay. And this 2 hydrogens is going to be a peak here. And I think that the 2 hydrogens that are on top are going to be 1 peak. And then the 2 hydrogens on the bottom are going to be a separate peak. So let's count up those. We have 1 here, 2 here, 3 here, 4 here, and 5 here. I think we're going to get 5 peaks for that. Okay. Ooh, symmetry again. And let's see. Okay, we have sp3 hybridized. So we don't have hydrogens on either one of those. So let's see, we're going to have this signal here is going to be one signal. And that's symmetrical. Okay. This here is going to be another signal, and those are symmetrical. This signal will be unique. Remember, we don't have hydrogens on either one of those. We don't count those. These are going to be the same, and this last one is going to be the same. So if we add those up, we have one signal for those methyl groups, one signal for this sp2 hybridized carbon with a hydrogen on it. So that's going to be 2, this is going to be 3, 4, and 5. And again, 5 signals for our proton NMR. Okay, so let's go ahead and start picking our carbon NMR. How many of these signals for, oh, yeah, we're going to do carbon NMR for these. And that should be a little easier because we don't have to worry about hidden hydrogens. So we're just going to go 1, 2, 3 because they're all different. So we're going to have 3 for that one. Okay, let's go ahead and do 1, 2. Now those are going to be the same, remember, because they're symmetrical. We have symmetry in this molecule. So we need to think about that right there. We have this one, and then we have this one here is unique. So we're going to have 3 signals for that one. Okay, so let's see, these 2 methyl groups are going to be a signal here. On C, these 4 are all equivalent. Okay, but we still have one more. We got to remember this, we're doing carbon NMR. So we have 3 signals for carbon NMR because of symmetry. Okay, I think we're going to break that symmetry down here in the next one. Okay, so let's start with this one. We're going to start with this methyl group. There's one signal. This methyl group is a different signal because it's hooked to a CH2 and this one's hooked to the benzene ring. This is a different signal. I think that because that could be a different signal, and might be the same signal as this one here, but just to be on the safe side, yeah, because they're hooked to the same thing. They're both hooked to carbons, they're both hooked to, so that should be the same right there. Let's go, then that makes these 2 the same, and it makes these 2 the same. So we have 1, 2, 3, 4, 5, 6. So I think we get 6 carbon peaks on that one. All right, let's go to E. We have 1 here because it's the only one with the bromine. 1, 2 here because those are next to it. We have these 2, which are next to it and symmetrical, and then this last one. So we have a total of 4 peaks. So this one, the next one's going to be kind of hard. Let's see, these 2 are the same. Oh, did I do those? I did not. We have to add 2 more peaks to this one right here. We have a hydrogen here, and we have these 2 methyl groups here. So that means it's not 5, it's 7 for hydrogen. Okay, let's see if that's the same for that. So we have 1 peak there. Okay, this peak is different than everything else. This peak is different than, oops, let's do a different color here. Make sure we're, so we're going to start with red. This one right here is the same as this one right here, because if you go to, it's got it connected to a carbon on either side, it's connected to an oxygen. So I think those are the same. Then these 2 are probably the same. And this one is different because it's next to the, so let's count those up. 1, 2, 3, 4, 5, 6. So we have 6 for that one right there. All right, let's go for this one. Let's see, those 2 methyl groups are the same for a carbon signature. These 2 are the same. And these 2 are the same. And these 2 are the same. And these 2 are the same, but we have 1 more. We have 1 more. They didn't have hydrogens on them, but we get to count them this time. So let's look at those. Let's see how many we have. We have 1, 2, 3, 4, 5, and 6. We have 6 carbon signatures for that. Okay. So let's go to the next one. We have, again, symmetry here. And we're looking for carbons. So we only have 1. And these are the same 2. And then our last one is 3. So we have 3 for that. So one of the things to look for if you have like a very simple or symmetrical system, like a 2 and 2, or a 2 and 4, is you might have a ring. Okay, so we'll have to look for that in different ones. Okay, so let's see. Carbon, we're going to do those are the same. Those are the same. These are the same. These are the same, which leaves this one and that one. So we have 1, 2, 3, 4, 5, 6 carbon signatures for that one as well. Okay, so now that we can pick out the number of signals we have, let's go through and try to do some spectra. Okay, so we have just a proton NMR. They tell us that we have a empirical formula of C5H80. Okay, so let's see if we see all of them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have 6, 7, 8, 9, 10, 11, 12. How do we get 12? Oh, it is 12. This one's wrong. We have the C5H12. So we're looking for something with 5 and 12. Okay, so now we have the classic pattern here. This is an ethyl group right here hooked to an oxygen. And notice these 6 are a singlet. So that means we have two methyl groups hanging off something, but it's not hydrogen. There's no hydrogen on there. We have an OH group because this is all by itself and it doesn't split and it's broad. Okay, so we have that. We have this fragment here. So it's next to an oxygen. Ooh, you know, it's not actually on an oxygen because it's not over here next to 3. So that means it has to be 1 away from an oxygen maybe. So maybe like that. Let's see. And then, so we have 1, 2, 3 carbons. So we only have 2 more carbons. Okay, if we do a methyl group here and a methyl group there, that means there's no hydrogens on this bond. Okay, let's see. We have an ethyl group right here. So this is this one, and then this is this one. Let's see, this H is going to be that one right there. And then look, these can be this one right here. There's no hydrogen splitting it. We have 6 protons with no hydrogens. So I think that our answer is H and then nothing. Okay, see how we look for things we know. We know the fragments that we have, like this is the perfect pattern for a 3-2. This means we have no hydrogens nearby, those 2, so that means 2 methyl groups are symmetrical. And this was our OH. And so by getting our fragments and putting them together so those fit, I think we got our answer correct. All right, explain how you can tell the difference between these two using a spectroscopic method. All right, and so this one is proton NMR. Okay, so if we look at this, we're going to get a singlet here. And that singlet's going to be around 2.5. This singlet here is going to be around 3. Okay. These is going to give a quartet up near 3 and a triplet down below near 1. This is going to give a quartet at 2.5, and this is going to give one at 1, and it's going to be a triplet. So all we have to do is compare so this one's going to be at 2.5. This one's going to be closer to 3. So all we have to really do is compare the singlets on the shift, and that should tell us which compound we have. Okay, all right, and this one, let's see what we have here. We're gonna have it kind of, well, this one's probably gonna, okay, we have carbon NMR. Okay, so let's think how many peaks we would have here in carbon NMR. We would have 1, 2, 3, 4. So this would have 4 peaks in carbon NMR. All right, we'd have 1, 2, 3. Oh, and then that's symmetrical this way. So we'd have 3 peaks in carbon NMR. We'd have 1, 2, 3, 4, and 5. So we have 5 peaks by carbon NMR. So just by carbon NMR, if you have 3 peaks, it's this one, 4 peaks, it's this one, 5 peaks, it's this one. Okay, so I'm glad we learned how to figure out where all our hydrogens are and what their splitting patterns would be and how many carbons there are. Ooh, now we're going to have a little bit harder time. We're going to try to compare and contrast some things. Okay, so let's think what we know. Okay, so this right here is a CH3 group next to no hydrogens because it's a singlet. Okay, we have a 2 hydrogens and a 2 hydrogens. And gosh, they look a little bit messy, not pure CH2s, or you can't really quite tell. Then we have a triplet with 1 hydrogen, but look where it is. That means we have to have an ethylene with actually only 1 hydrogen on it. We have to have that kind of structure somehow. So we have that as a fragment. Okay. And then so we have a CH2 and then a CH2 next to something, and then we have a methyl group by itself. Okay, let's see what else we see. All right, let's go down here. Okay, so we have our CH3. So we have at least 1 CH3. Okay, and we have 2 CH2s, and they're shifted a little bit. They're not like hydrocarbons. We have a carbon in a double bond that has no hydrogens on it. We have a carbon in a double bond that has 1 hydrogen on it. Ooh, that agrees with what we saw up here, right? It agrees with what we saw up here because there's only 1 hydrogen in that 6 ppm ring. So we have that. But then we have, we have to have a carbonyl here. Okay, it's above 200. So that means it's probably a ketone or an aldehyde. So let's look at the IR and see if they can tell us anything. Well, it looks like we definitely have a carbonyl, and it's a high one, but we definitely have a double bond, which is this one right here, because that's the only thing in that range. And then we might have a little, I don't know exactly where that 300 was, so I'm not sure if there's a vinyl hydrogen, but there must be because there is one in the proton in the carbon one. All right, so let's put these fragments together. Okay, so we have 1, 2, 3, 4, 5, 6 kinds of carbons. Okay, but that means we have to have like a CH3 here because it has to be by itself and not near any hydrogens. But that only gives us 1, 2, 3. So we only have 1, 2, 3, 4, 5. So we only have 6 carbons to deal with. That means we need to somehow fill this out right here with 3 carbons. So, but we definitely need to have one of them be a carbonyl. So what about CH3? Let's put a carbonyl here, put our hydrogen here. We only have 2 more carbons. And this hydrogen has to be next to 2 hydrogens because it was split into a triplet. So there has to be that there. And then, oh gosh, the only thing left to do, because we only have 2 hydrogens and 2 hydrogens, is we have to make this 2 hydrogens. So we got this from the carbon NMR. We got this from the proton NMR. We got the vinyl group only has this from the proton and the carbon NMR. We got these here because this was split into a triplet, and these 2 were split into multiplets. And when you have things in a ring, maybe the up and down does the multiplet split. So I think this structure agrees with all of the evidence we have. CH3, and then close the ring. So we have a total of a 5-membered ring, So we have a 5-membered ring with a ketone with an alkene. So that'd be an enone. And so we have cyclopentenone. Okay, that's kind of hard. Okay, but we looked at our evidence, we got our little fragments together, and we put them together the best way we could. Okay, so just like that, we have 2 methyl groups here that are probably sticking off something like that because they, let's see, oh, and that's a doublet too. So that means we have 2 methyl groups right here with a hydrogen here. Okay, six hydrogens with a doublet means that then we have something else over here. I don't know what that's. Okay, we have right here. So that could be a single hydrogen, and it could be bonded to an oxygen or a thing with an oxygen, or a single hydrogen that is adjacent to a double bond, or a single hydrogen adjacent to a halogen. But they didn't say it was any halogens in here, did they? So let's see, we have this pattern here. When we talked about benzene rings, we said that if you had a substitution pattern that was like this, you get a doublet of doublets. So I think that's what this is here. And then we have 1 hydrogen way up here. Gosh, there's only 2 things that are up there. That's the aldehyde and the carboxylic acid. So we must have an aldehyde here somewhere. But let's make sure, let's go look at the carbon NMR and see what we see. Okay, so we have a methyl group by itself, a CH by itself. Ooh, that supports this fragment. Okay, then we have benzene, and because it's right here, and we have 1, 2, 3, so we have something that could be symmetrical. So that means it could be this. Remember when we were picking the benzene and it was symmetrical like this, we got 1 for this, 2 for that. Oh, and then, so, oh, it's not symmetrical, but it's definitely substituted in this pattern, which means there has to be 2 different things on this different sides. That's how we got the 3 signals. 1 signal, 2 signal. And it looks like there's a signal here that might be missing. It would be the 4th one. So that means we probably have X and Y on there because they're different. And then we have a CH way up here. So that's telling us that it's definitely an aldehyde because there's an H on it and it's up in the carbonyl range. So it definitely has that. So we have an aldehyde and we have this fragment here. Okay, let's look at our thing here. Okay, we definitely have the benzene here. We have the carbonyl here. And it looks like we have stuff above 3000. So it looks like we definitely might have the benzene ring. All right, so let's try to put this all together. So we have an aldehyde, and those hydrogens are not near any other hydrogens. So maybe that. And then what was our other fragment here? Oh, our other fragment was something bound to that. So let's put it here because it has to be opposite each other, because that, and then that. And then that, of course, gives us the doublet. This gives us multiplet. This gives it our doublet of doublets right here, and our single peak here. So yeah, that satisfies all those rules. Okay, so I hope you are getting used to doing these things and identifying this. These 2 problems here are also pulling in IR. We're going to continue to do that through the end of the semester. So hope to see you soon in another homework chapter. All right, talk to you later. Thank you and bye.